Professor Kang is a professor in the Department of Physics and Astronomy at University of California. His other affiliations include faculty member at Bhaumik Institute for Theoretical Physics and Center for Quantum Science and Engineering at UCLA, associate member in Center for Frontiers in Nuclear Science at Stony Brook's University and Brookhaven National Laboratory. His research interests are primarily in quantum chromodynamics and strong interactions. Sorry if I butchered this, and their applications in high energy nuclear and particle physics. So today, during his talk about fundamental structure of matter, Professor Zhongbo will answer the question, what makes up all the matter around us, such as stars, human bodies, etc. He will walk us through how humans discover these different layers of structure that matter and how scientists are moving forward in this quest. So, Professor, thank you so much for joining us today.
Yeah, thanks a lot for this interesting opportunity. I'm very happy to be here. So we're going to talk about some fundamental structure of matter. This is the main subject in nuclear physics and particle physics. So it's one of the fundamental directions in physics. Now, okay, so yeah, we're always wondering about our origin, right? What are we made of? Like stars, our human bodies, and our own universe. We always have these questions. Well, to answer these questions, we have to first go through a little bit basics, like setting up our skills for such understanding, right? So these days, of course, it's COVID. During the pandemic, we're always talking about, oh yeah, there's a guidance. We have to be apart from each other, like 6 feet. So what is 6 feet? 6 feet is roughly like 2 meters. So this is typically your height of a human body. So we're talking about, so we're starting with 2 meters, and then we continue break it down into very small scales. So if you starting from 1 meters, if you be like smaller by 1,000 times, this becomes like a millimeter. Right? So it's 10 to the minus 3. If you're done by 1,000,000 times, this is called 10 to the minus 6. This is called a mu. This is mu m. So for example, our hair, if you like stick your hair and you find that our hair is roughly like 100 mu m, okay, 100 micrometers. Right? You can go further down, and you might heard a word called a nanotechnology. Those are talking about nanometers, that 10 to the minus 9, okay? And you can go further and talking about picoseconds. Those are the time, it's 10 to the minus 12, okay? This is called pico. And down to the end, and there's some scale called 10 to the minus 15, right? So go 15 orders of magnitude smaller. This is called a femtometer. And today's talk, we eventually will go to the level of called femtometers. At the femtometer, you will find it out all the matter are made of the same, or same building blocks. Those are what we call fundamental particles. Now, so the very first thing that we wanted to do is let's zoom into our hair, see what happens. So this is an interesting picture. And this is our hair, okay? If you zoom really small and you see, oh, this is a hair. And you go further, you will see cells, okay? You can see cells inside the hair. And there's a different layers of fibrin. And further goes, you can call keratin. Okay, any questions? So keratin is the interesting thing it's one of the protein. It's typically the people like doing biology and chemistry, and they will study around this level. For nuclear and particle physicists, they wanted to go further and study even more fundamental structures. So this interesting movie is going to tell you how we can go further and understand those fundamental structures. So let's go ahead and try to study this. Can you guys hear the sound? Great. You starting breaking down every time, like breaking down by 1 order of magnitude. The hair is 100 micrometers. Go further is a cell, it's 10 micrometer. One of the protein, typically biologists will stop over here. This is atoms, carbon, oxygen. Chemistry will stop here. This is one of the carbon atoms. Those are electrons. Electrons are freely in space. Go further. It's very, very tiny. So tiny, you couldn't even see it. This is the atomic nucleus. And then that's the time where nuclear and particle physics starts to perform the research. Those are protons and neutrons. Inside the protons and neutrons, you have even more fundamental particles. Those fundamental particles is called quarks. As you can see, this is the level, the size of the proton is 1 femtometer. As I said, a femtometer is 10 to the minus 15 meters, right? 10 to the minus 15 meters. So this is roughly the structure. You go from the hair around 100 micrometers and up to 1 femtometers, 10 to the minus 15. It's really, really small ones, okay? Oh, I don't know what happens. Let's go back. Yeah, go back to present. Okay, so this is our current knowledge on nuclear and particle physics. Any matter, and it can then go to the molecules. So this is typically when chemists stay at over here. This is the order, the size of the molecule is something like around 10 to the minus 10 meters, right? And you go further inside the molecules, they have atoms. And so the atoms, there's electrons outside, inside, there's a nucleus. So this nucleus is 10 to the minus 14 meters. Okay, 10 to the minus 14 meters. If you go down and this nucleus break it down into protons, which is positively charged, and the neutrons, which is electric neutral, doesn't carry any charge. These two guys have the size 10 to the minus 15 meters. This is what called 1 femtometers or 1 Fermi, okay? And to go further, you have those fundamental particles called quarks and gluons. These days, so nuclear and particle physics is studying the interaction between these fundamental particles, quarks and gluons. They are binding together by these curly lines. It's called gluons. It's kind of glue them together. So let's go back to understand how exactly the physicists actually figured out these structures. So of course, from the very beginning, and a human and ourselves are very curious about our nature, about the structure of the matter. But until only most recently, like around 18th century, and people starting to understand this in a more scientific basis. So in 1803, and Dalton for first time and proposed these atoms. The idea of the atom called all matter are made of extremely small particles called atoms. After that, and the next level, it goes into almost 100 years until we finally discover atomic nucleus. So this interesting YouTube video will tell you that story.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So this one
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered.
So let's go further.
In 1910, Rutherford.
So now, so from these experiments, they find it out there must be something very massive, okay, to deflect those alpha particles in a very large angle. So they're really massive, but yet they're really small because the probability those particles get deflected is really small. Only very few particles get deflected. So that means this whatever inside these atoms must be very massive. And secondly, it's really small. So this is laid down, it's called atomic nucleus. And interesting, you'll find that even though it's so small, it's smaller by 4 orders of magnitude smaller than the atom's size, okay? This atomic nucleus is 10 to the minus 14. The size of this atom is 10 to the minus 10. So it's 4 orders of magnitude smaller than the atom's size. And so this, the scientist that discovered this is Rutherford back in 1911. Okay, even though it's so small, but you'll find it out for the entire atoms, the 90% of the mass of this atom is carried by this nucleus. Okay, by this nucleus. So because of that, these days you always heard people saying the 90% of the visible mass for the universe, of the visible universe, are carried simply by atomic nucleus. Okay, the electrons is so tiny. So this is very interesting sculpture in China, in Shanghai. Okay, to characterize this interesting fact. And later on, and 8 years later, Rutherford himself again discovered another smaller particle called protons, which is part of the nucleus. And his student is Chadwick. He's a PhD student and later on 14 years later, okay, after he already graduated, he learned on techniques from his PhD advisor, and for 14 years later discovered neutrons, which is also inside atomic nucleus, okay. You go further, okay, and once you know there's protons and neutrons inside nucleus, and then you are starting to want to understand whether these guys has any size. So the scientist down in Stanford through the particle collisions from these scattering experiments. Eventually, they come out with a number. So this is the professor back at that time actually figured out this. So they find it out that the size of the proton is something around like 0.8 Fermi, 0.8 Fermi. So Fermi is 10 to the minus 15 meters. So this guy by itself also has size. Once you know it has size, and the theorists, yeah, they're going to be very busy to come out with a new theory to figure out what's going to be inside this protons and neutrons, and also other particles. And back in that time, Gell-Mann is a young physicist from Caltech, and Zivig is another young scientist from Los Alamos National. They come out with this model called quark model, saying each of the protons or neutrons, they are simply composed by quarks, like 3 of them, right? Now, and of course, once the theorists ask the next question and experimentalists, they wanted to figure out how exactly you can discover and to find and to looking for these particles inside a proton. The way you do it is very simple. If you want to know what's inside your phone, how do you do it? You smash your phone and then you see what's inside, okay? It's exactly the same idea. You using some particle, smash your protons, and then by looking at the debris of these collisions, and you're trying to figure out what's inside, right? So there's a lot of experimentalists, these 3 ones, and the theorists, Feynman and Bjorken, and they're working together eventually to figure out what's inside these protons. Those are called quarks. So this is in the modern days, okay, these days, we're using exactly the same idea. We're trying to smash the particles and to figure out what's inside. So this is called a particle collider or called a particle smasher, right? This is a very interesting one. The largest one is done in CERN. This one circumference of this collider is 27 kilometers. It's down beneath, like 175 meters beneath France and the Switzerland border near Geneva. Okay, this is the interesting collisions you will be able to see. So those are the 2 beams of protons and accelerating to be really fast. So these blue ones are supermagnets to accelerate those particles to be really, really fast. So fast and moving almost to the speed of light. Okay, this is our proton, and they're in a tunnel. They're starting to colliding with each other. There's another proton from the other side of the beam. They're moving, and then you're trying to make them collide with each other. Boom! And then there's so many particles coming out, and by looking at this distribution of these outgoing particles, you can try to figure out what's inside the protons. So this is these days. This is how we actually figured out the structure of the particles. Now what? So what's the next step? Now you know there's some particles inside it. Now what do you do? Right. So the next thing is, so imagine how astronomy actually trying to figure out to broaden our imaginations. The way you do it, you take an image of a really beautiful our universe, and sometimes you take an image of the black hole, and sometimes you take an image of the galaxy system and then the stars and everything. By looking at those interesting images, you're trying to figure out the dynamics. That's exactly what we do over here in nuclear and particle physics. You know already inside there's fundamental particles, quarks and gluons, and grouped together by those gluons, right? And so we want you to also take an image in the protons and in the fundamental particles in those quarks and gluons. So this is these days we want to image in a proton, okay, and trying to figure out how those quarks are and the gluons are distributed inside the particle, both in the position space and also in the momentum space, how they're actually moving and how they coordinated and how they evolving through energy through time. Okay, so this is a very complicated picture and coming from our serious imagination. And we need to experiment to verify this can be, this will be true or not true. Right? So to build, in US, we're going to build a new collider. It's called ion ion collider. It's going to be built at the Brookhaven National Lab down in Long Island in New York State. Currently, at this time, they're hosting a collider called a relativistic Hera ion collider. So by 2031, and this collider is going to be upgraded and repurposed and rebuilt into a new collider called an electron ion collider. Electron ion collider, it's you're using a polarized electron colliding with either a proton or heavy nucleus to try to understand the structure of the proton nucleus. So to a large degree, and you can think about this electron ion collider, it's the world's largest CT. It's a scan. You perform a scan to provide the image of the proton and nucleus. Right? So this is one of those interesting images come actually from our students' simulations. In the momentum space, you see it's kx, ky in the transverse momentum distributions. If it's unpolarized, it's symmetric. If you have some polarization, it's going to be distorted. Okay, so hopefully in the future, we'll be able to verify such a theory picture. So last 1 minute, let me see why do we want you to study quarks and gluons? If you remember what I said, there's quarks and gluons inside the nucleus. It's much smaller than the size of the atom. It's 4 orders of magnitude smaller, but yet it accounts for 99% of the mass. Okay, imagine these days the electricity. Okay, we really realize our electricity made our modern life possible. The reason where the electricity actually worked is because of the progress in the fundamental science. We are able to understand and manipulate the electrons' motion. Okay, those are tiny electrons, right? So, however, those electrons only counts less than 1% of the potential of the energy. Right? So now you can ask the question: what if we could study those 99%, the quarks and gluons, in exactly the same way as we do for electrons? Then we would have the possibility to unlocking the remaining 99% of the potential, the matter around us. Nobody knows the implication, so that's why we say the implications are unimaginable. So, thank you.
Thank you so much, Professor. That's very, very true. Thank you, Rokas. I see you. Truly, yes, this is something that's very frontier, and the future is your guys' to make, right? The potential is unimaginable. And Professor, thank you for charting us into what's possible and what we can look into in the future. How do you guys, Cam says thank you. What do you guys think of this presentation? You know, how do you feel right now, guys? We're 2/3 way there. Okay. Shoham said thank you so much. I enjoyed the presentation. Same. I love the videos. They're very, very intuitive and visual, and just allows us to understand a lot more about what's going on. Oh, okay. We got some questions going on here, Professor, if you don't mind me
yes,
saying them. So David asked, can you tell us about the 3 types of quarks, please?
Yeah, so fundamentally, there are 6 types of different quarks, not just 3. But in order to just form like a protons and neutrons, you simply need 2 types of quarks. One is called up quark, and the other one called down quark. So up quark carries positive charge, and down quark carries a negative charge. So that's why we have we need 3 quarks to form a protons. Right? And then similarly for neutrons. So for protons, you need 2 up quark and 1 down quark to form it. For neutrons, you need 2 down quark, 1 up quark to form it. So those are, hopefully that's what you mean by 3 quarks, right? But in total, we actually have 6 fundamental quarks.
Okay, 6 quarks, 3 for proton, 3 for neutrons, right?
Yes.
Okay, thank you. David said, excellent, thanks. And this question from Doug. Okay, so we got time. Do you mind answering maybe 1 or 2 more questions, Professor? I think.
Yes. No.
Okay, thank you. Thank you for your time, by the way. So Doug is asking, can each quark be a separate universe with galaxies, planets, and beings? Is it possible that within this little quark, there's so much more?
So so far we don't know yet. There's definitely some theories is thinking about that way. So like each of they think about like each of the like a protons as their own universe. But of course we don't know yet. The problem, counting the difficulty is we cannot really isolate those quarks. So there's some interesting effect called confinement, which is actually one of those 1 billion questions in math and in physics, and it's unsolved. The next question is simply saying why the quarks like to always stay inside the protons and they never come out. So so this is one of those interesting questions. We actually don't know so much about how those quarks are actually located inside the proton, and since they never come out. So it's not like an electron, you can actually observe them, and you immediately can identify the position and momentum. But for those quarks, it's very difficult since they never come out. So this is why we have a lot to learn about them. This is one of the reasons we're going to build this electron ion collider.
Yes, yes, and that is for us to. That's for you to, explore. That's for you to explore, Doug. Hopefully, in future, you'll be the one that finds universe within universes, right? Thank you, Professor, for explanation. Let's get one more questions in. Does anyone want to ask a live question where you unmute yourself and ask? There's a couple really good questions, so I don't know what to pick, but anyone wants to unmute yourself and ask a live questions? Maybe some questions here is from Aria or, oh, Rohan raised his hand. Yes, Rohan, go ahead.
What's the smallest type of matter?
That's a very good question. So these days, there's a scientist that has a model called a standard model. And yeah, so for the smallest matter and the current at the laser stage to form our body is basically quarks and electrons. So those are the smallest. And we don't know yet when a quark can be even has some even smaller structure. That question we don't know yet. But as far as currently theory, current experimental data concerned, it's just simply the quarks and the electrons are basically composed of our body.
Okay, thank you.
Yeah, great.
Thank you for the question. Okay, thank you guys. Thank you so much, Professor, for your time and your explanation. We're going to close the breakout room soon, and we have more talks after.